Alright, so read example 2 here. We have a Ferris wheel. The radius of the Ferris wheel is 10 meters and it makes one complete revolution every 20 seconds. The bottom of the wheel is 1 meter above the ground. Now that's important because that tells us something about the lowest point of our graph. The wheel, if we just want to make a quick little diagram, think of a Ferris wheel sort of propped up off the ground. We know that the radius is going to be 10, so that the diameter is going to be 20. Why is that important? Well, the first thing we're going to do, just like in the first question, let's give this a title. We'll just call this the Ferris wheel. And along the bottom we have time. Along the side we have the height. Think of your height above the ground as you're riding this Ferris wheel. So we'll say height above the ground. And now let's look at the information. Draw a graph to represent 2 full revolutions, assuming that the rider gets on at the bottom. Now that is important because it tells us where we're going to begin our graph. So at time 0, you've just stepped on the Ferris wheel. Where are we going to put our point? Well, if you're just stepping up onto the Ferris wheel, that means at time 0, you are 1 meter above the ground. So this is where we're going to start. If the radius is 10 meters, let's do what we did before. Take your pencil and draw me an arrow to represent 10 meters. So as the time goes on, you're on this ride, you get higher and higher and higher until you reach the midpoint. So you're halfway up to the very top. We know that this point, this is an important point because this is our axis. Again, draw your dotted line. The axis is going to be 11 meters. We go up another 10, I won't show that arrow, and we're going to get 21 meters above the ground. At 21 meters, that's the highest point of our wheel, and I can show that here in a different color. That's all the way up there. Okay, that's the highest point. There it is. So we have to create this function. It gives us the period. It says that one complete revolution occurs every 20 seconds. So again, down at your bottom of the x-axis, let me change back to red here. I want you to go about halfway, and I want you to show me about 20 seconds here. So I'll write that on top. 20 seconds. If we want 2 revolutions, then over here we're going to have 40 seconds. So here comes the question. Is this going to be a sine wave or a cosine wave? Well, look at the starting point. This is different from example 1 because our starting point is not along the axis. The starting point is actually at 0, 1 because we're getting on the Ferris wheel at that point. So our wave that we're going to draw is going to be a cosine wave, which is going to start at 1 meter. We are going to, that's not what I wanted to do. We're going to start here, we're going to go up, we're going to reach a maximum point, and then we're going to come back down. Okay. So that's a very rough sketch of a cosine wave. Now imagine this is going to continue. I'll draw 2 cycles here, all the way up and back down, and again, that's just going to keep on going. So again, these aren't very even, but you get the idea. These cosine waves. Now this again, these may look different from the original cosine wave that we used to draw. The first cosine wave that we drew started at the top and went down. Now that's going to be important when we write the equations. So the graph right now will stick like this. What we want to do is create the equation. So the tricky part here is that it's asking for a sine function and a cosine function. We're going to do the cosine function first because that's what we have. That's what we've drawn. So let me just get rid of some of this side stuff here. And let's go to black, and we're going to start with, I'll put B, a cos function. We need to do the same steps as in the first example. I need A, K, D, and C. So amplitude, what is the amplitude? Amplitude, again, this distance here, that's A. A is 10. K, we'll do the same thing as before. 360 divided by the period, which is 20. When we do that, we get 18. D, again, go to your starting point. Are you starting along the y-axis? Yes, you are. So there has been no phase shift. D is 0. C is your axis, which is 11. So we can now write this equation as y equals 10 cos of 18x plus 11. Now, one more thing we have to do. I mentioned before that this cosine wave actually opens down. Well, I want you to think of the original cosine wave that we have. Now, just to make it stand out, I'm going to use a bright yellow here to show. A cosine wave that we're used to seeing looks, and I'll draw just a little sketch of it over here, looks like this. So it starts here, it opens down and comes back up like that. That's the cosine wave. That is not what we've drawn here. It's actually flipped, and we call that type of flip a reflection. We have to show that reflection in our equation, and you're going to show that by adding a negative, okay, in front of the amplitude. Whenever you see that difference in graphing pattern where the wave looks upside down, think of it that way, it's an upside down wave, we have to add that negative in front of the A. So this is your cosine function. Now, the next part is to draw or to write an equation to represent the same wave but as a sine function. Now, this is where it's going to get a little bit tricky. What I want you to do with your pencil, and again I'm going to do this in the yellow so that it stands out. With your pencil, I want you to go and put a point on your graph just where I'm putting a point there. So you're on your axis, but you're slightly moved over. And the reason why we want to do that is because I want to highlight, and I'm going to do this in yellow right now, what looks to be a sine wave. That's that there. Same function. I haven't changed the function. I'm just looking at it so that it resembles a sine wave. What you want to do now is repeat the process we did with the cos function and find an equation to represent what I've highlighted here in yellow. So as a sine function, ask yourself the same questions. What's A? What's K? What's D? And what is C? So I'm just going to go to a new slide and we'll write that out here. So as a sine wave, right? Keep your picture in front of you. Let's think of A. A is still the same. The amplitude does not change. So we can keep that as 10. K, well, K doesn't change either because the period is still the same. It still takes 20 seconds to complete one revolution. So we're going to keep that as 18. D. Now, here's where we have to be careful here. Let's go back for a second. The D value is going to be greater than 0 simply because we don't start along the y-axis. The question becomes, where has my starting point moved from the y-axis? How far did I move right? This is where we have to do some math. If it takes 20 seconds to complete one cycle, well, I know that my halfway point exists here. That's 10 seconds. Well, if I moved halfway between 0 and 10, I moved 5 units to the right if I'm looking at my sine wave. So we have to show that. D is 5. My C value is the axis, which is 11. So we can take this information now and write it as 10 sine 18 bracket x minus 5. Remember, it's minus 5 because it's the opposite direction which we write. If it's moved 5 to the right, I have to subtract the 5. And then I can add 11. Notice that I did not have to put the negative in front of the 10, because this sine wave looks as it naturally should. A sine wave goes up, then comes down, and meets back at the axis. So there's been no reflection of this sine wave. It looks quite natural. So there you have it. You have two equations to represent the same picture. Go back and have a look at this sine wave again. It is tricky. Remember that the phase shift has to occur if you're going to write this as a sine function. You can't just take the same d value as you did with a cosine function. The next step is to try example 3. Example 3 is almost identical to example 2. What we've just done, it just deals with slightly different numbers. So make sure your graph is nice and clear. After you've completed example 3, I'm going to post the full solution on the website and you can compare.